I'm namely the presenter. Our team has carried out a project on improving the image classification of white blood cells using AI. When training an AI model, the amount of data greatly influences its performance. However, in the medical field, it is difficult to obtain enough high-quality data due to privacy concerns and other issues. Therefore, our team aims to improve the performance of the image classification model by increasing the amount of data using a GAN model. Let me introduce the models used in this project. First, we use the GAN model to generate images. Second, we use the unit to increase the classification performance of the model by extracting the features of the image through segmentation. Now, I will explain the GAN algorithm. The generator receives a random noise vector and generates an image by gradually increasing its resolution through transposed convolution layers. The discriminator receives the fake image generated by the generator, reduces the image's resolution through convolution layers, extracts important features, and determines whether the image is real or fake. Based on the discriminator's determination, the generator learns to reduce its loss to produce more realistic images. This competitive learning process between the generator and discriminator is often described as a two-player game. The system is considered optimal when the losses of both the generator and discriminator are close to 0.5. There are various types of GANs. For example, there is DC GAN, which is a deep convolutional GAN, and other types like unconditional GAN, conditional GAN, and super resolution GAN. We implemented a basic DC GAN. The structure of the model is as follows. The key difference is that we use transposed convolution layers for the generator and convolution layers for the discriminator. Both structures use the leaky ReLU to prevent the vanishing gradient, and batch normalization and dropout to stabilize the learning process. As the activation function, we use the tangent function to adjust the output to a range between -1 and 1. The detailed structure of the generator and discriminator is as follows. We used Atom as the optimizer and binary cross entropy as the loss function. When you run the model for the first time, Apple1 generates a random noise image as follows. If you continue training a GAN with this input, you will see the following images. Comparing the image at epoch 300 with the image at epoch 600, you can see that with more training, the edges of the cell become clearer and the background features are better captured. The image at epoch 900 shows a clearer background than before. At epoch 1200, not only are the background features well captured, but the cell nucleus is also clearly visible. Final result, there was a difference in the number of data per class, so some classes did not learn properly. That was the GAN description.
Hi, I'm Junhee Han, who is going to explain a Unet model and how we apply this model for segmentation of white blood cell. First of all, as you learned from the lecture, Unet is used for semantic segmentation. Semantic segmentation is dividing objects in the image into segments which have meaning. Specifically, it is predicting which pixel belongs to which class. As you can see the image below, the right one is an example of semantic segmentation. Every pixel in the image belongs to classes such as road, sheep, or grass. In this page, I'm going to give you an explanation of the principle of Unet architecture. Unet was built based on fully convolutional lake network. As you can guess from the name, FCN is a neural network that every 6 layers consists of convolutional layers. It is mainly used for segmentation. The left side of Unet is contracting path that captures a context of an image, On the right side, there is expansive path that does upsampling a feature map and concatenates with a captured context from contracting path. Concatenating layers of contracting path and expansive path makes that Unet can localize an image better. We can expect a segmented image like this after running on Unet. If you used a method like k-means clustering for this image, you probably couldn't get a proper segmented image that you want. To solve this kind of problem, you can train a Unet model with images and ground truth. There are two images in the center. Left one is an image and a ground truth that we used for training on Unet. And right one is an object showing that we want to label white blood cell images like this. We got this dataset from GitHub, and there are 100 pairs of images and labels of white blood cell. And from this page, I'm going to tell you about the structure of Unet we've built. The input size is 128 by 128 with 3 channels. If an image was put into the model, it will go through first convolutional layer and each input becomes 24 outputs. Before going further, I have to say that after every convolutional layers, batch normalization and value is applied, and after every max pooling, dropout is applied with a rate of 0.5. Moving on, this slide shows you that max pooling is being applied after 2 convolutional layers, so the size of the feature map shrinks from 128 by 128 to 64 by 64. Next, 2 convolutional layers, batch normalizations and values, output becomes 128 by 128, which was 64 by 4 by 64 before. On second max pooling, size of a feature map decreased in half again. On third convolutional block, outputs increase, and so on. After contracting part, the data will expand through expansive path or decoding. You can see the size of a feature map grows from 8 by 8 to 16 by 16 after transposed convolutional layer. In expansive part, after every transposed convolutional layers, it concatenates a feature map with the feature map captured in contracting part before, and also dropout is applied with the rate of 0.5. Similar to contracting part, this process is repeated until the size of a feature map becomes equal to an original image, in this case 128 by 128. A feature map gets bigger and bigger after going through transposed convolutional layer, and output gets smaller after going through 2 convolutional layers. So this is the loss graph after 100 runs. It wasn't trained perfectly. I think the reason why the loss isn't low enough is that we only used 100 images and labels to train and Unet and didn't apply any augmentations to images to train. So this could cause overfitting. Although it didn't go as well as we expected, we made a few segmented white blood cell images with this dataset. There are over 17,000 images and 10 classes. We choose arbitrarily neutrophil, eosinophil, lymphocyte, and monocyte. This is the result that we make segmented images with neutrophil and monocyte. The left one is actually quite well done, but the right one isn't good enough. If you enlarge the image, the bottom of the nucleus isn't connected, but in the predicted label it is connected. The lymphocyte image on the left is decently segmented, but the eosinophil on the right isn't well divided in the way we wanted. In my opinion, if we had enough time and resource to build the model, this problem could be solved by collecting more images and labels and applying some augmentation.
Finally, I will show you the results of classifying images generated by GAN using Unet. These images are Unet classified images of the neutrophil class created with GAN. This image shows the Unet classification of the monocyte class created with GAN. Unlike the neutrophil class, the monocyte class was not properly segmented, likely due to differences in the amount of training data. Among the images generated by GAN, those of good quality were segmented well as expected. Although our initial goal was to compare the improved image classification performance after training Unet with the generated images, we couldn't experiment with this due to time constraints. We will finish the presentation and take questions.